welcome to the 16th lecture of the course turbulence. So, let me start with brief recapitulation whatever we have done in the last class. So, we considered the vorticity equation as this. Okay. So, this is the change of vorticity, this is the change local change of vorticity, this is change due to the convection, and this is the vortex tracing and tilting term as I have mentioned, and this is the vorticity diffusion term. Okay. So, that is what we have derived first, then what we did, we considered this Reynolds decomposition, okay, and with this this decomposition has been then put in this particular equation, then we took the time average, and after this procedure, this is the equation which we have got for the average vorticity change. Okay. So, this is the change of vorticity. Okay. The time part or the local part is 0 because we have considered the stationary flow for which the change of omega I with respect to time is 0. So, and this is your this velocity and vorticity interaction term, okay, and this is your change of vorticity due to the stressing of the mean vorticity by the mean strain rate tensor, and this is the change of vorticity due to the interaction between the turbulent vorticity and turbulent strain rate tensor, and this is the diffusion of the mean vorticity. Okay. So, now in today what we are going to do, we are today actually we are going to proceed with this equation onward. So, we would like to find out the enstrophy equation, the way we found the energy equation from the average Navier-Stokes equation, mean kinetic energy equation from the average Reynolds stress or averaged Rans equation. In the same fashion, we will multiply this equation by omega I, and let us see what we get. Okay. So, we will start with this equation, and let us say this equation is our equation 1. Okay. So, we are going to talk about the mean square vorticity or enstrophy, okay, mean enstrophy equation. Okay. So, mean enstrophy equation or mean square vorticity mean square vorticity equation. Okay. So, that is what we would like to find it out today. Okay. So, first what we are going to do, we are going to multiply this equation number 1 by mean vorticity omega I, and let us say what we get. Okay. Now, you see left hand side of this equation can be written as u j del half omega I into omega I, okay, del x j. And you see the first term we can write as del minus omega I u j omega I del x j. Then we have to to arrive at this particular term, we have to subtract or we have to add one term, that is your this. Okay. So, essentially the first term has been written in two parts. This is one part, this is another part, okay, plus whatever is there, let us keep it as it is. Okay. Plus this part, the viscous part of this equation can be written in two part, that is your half sigma I del x j minus nu into del x j. Okay. So, this is the way we can get this equation. So, this is the mean entropy equation, okay, or mean square vorticity equation. Okay. So, this is what the known as entropy equation, and in this equation we see the change of entropy. Change of entropy is due to all other terms in the right hand side. So, if you see this particular term, it is what? It is the transport term, it is transport of transport term. So, transport by the turbulent velocity fluctuation, okay, transport of mean vorticity by this turbulent velocity fluctuations, and this particular term, okay. So, this is our transport term. So, this particular term is known as transport, okay, transport of mean vorticity. This is this particular term can be called as gradient production term, okay, in anticipation with the same term with a negative sign in the fluctuating entropy equation. Okay. So, that is what we will come to this term once again, and this particular term your the production due to the mean strain rate tensor. Okay. So, production of mean entropy due to the mean strain rate tensor. Okay. So, this is also production. So, this term is also production due to mean strain rate tensor, that is capital Sij. Okay. And the next term, this is this is known as mixed production. Okay. So, this is known as mixed production because we will see similar term even in the fluctuating entropy equation. Okay. So, in this term if you look at, so it is actually production of mean entropy due to the fluctuating or turbulent vorticity and strain rate interaction. Okay. So, this is what is your mean or sorry mixed production term. We will come to this term once again when we will talk about the turbulent entropy equation. Okay. And this particular term is the viscous diffusion. So, this is the viscous diffusion term of the mean entropy, and this is the dissipation term. Okay. So, this is dissipation, keep it in mind. Okay. The last part is dissipation, and this is your the viscous diffusion. Okay. This is your viscous diffusion, and the last one is dissipation. Okay. So, this is what is our mean entropy equation, right. Now, we will see which terms are very important or which terms contribute maximum to change the entropy in the flow. So, that is what we would like to, if we would like to look at that particular aspect, then we have to first find out the order of magnitude of each and every term. Okay. So, if you find out the order of magnitude of each and every term, you see what we can do, we can write this equation once again here and find out the order of magnitude of each and every term. So, this is the transport term plus gradient production. Okay. This is u j omega I del omega I del x j plus capital S I j plus your mixed production term, that is omega I S I j bar, okay, plus two viscous terms, that is your nu del 2 del x j nu sigma I del x j del sigma I del x j. Okay. Now, if you would like to find out the order of magnitude of each and every term, then what we have to find it out? First, we have to know the order of magnitude of this. So, order of magnitude of this particular term, what it is, half this particular term is equal to del u I del x j. So, this is nothing but your del capital U I So, let me let me just write without let us say this is 1. So, if I consider this as 1, then this is going to be your del x 2 3, then del 3 2. Okay. So, basically this omega 1 or 2 or 3, they are the gradient of mean velocity. So, the order of magnitude, so from this you can find the order of magnitude of omega I is nothing but order of magnitude of this. So, that is u t, that can be considered as u t by L. Okay. So, order of magnitude on omega I can be written as u t by L. Okay. Now, you see what is this particular term, order of magnitude of this particular term. So, if you consider the order of magnitude, this particular term is nothing but your you can write this term as you see here. Okay. See here, this particular term has come from here. So, what is the order of magnitude of this term? We found this particular term is what? This u j omega I, this term we found in the equation of motion, and that particular term we showed that can be expressed in terms of gradient of Reynolds stress. Okay. So, this particular term, if it can be expressed in terms of gradient of Reynolds stress, then order of magnitude of u j omega I is what? U t square by L. So, order of magnitude of this particular term is u t square by L, and this omega I del x j is equal to your u t by L square. Okay. So, order of magnitude of this particular term then can be this is of the order of essentially u t square by ut square by L into this is your ut by L. So, sorry this one is ut square by L and this is ut by L and this is 1 by L. So, ut cube by L cube. Okay. So, this order of this particular term is ut cube by L cube. Similarly, order of this term is also ut cube by L cube. Okay. And order of this term, as it is clear, this order of ut cube by L cube. Okay. What is the order of this term? Once again, this particular term, if you can remember. So, this particular term, what is that? Omega I S I j. Okay. So, omega I S I j is equivalent to omega I del u I del x j. That is what we have done in the last class, right. So, essentially this is just 1 minute, this should be omega j. Okay. There is a mistake here. So, this should be omega j because we are multiplying by omega I. Okay. Because why? So, this should be omega j. Okay. This should be omega j, I am sorry. Okay. Correct, there was a mistake. So, this should be omega j. That means, you see this is omega j and this particular, that means omega j. So, this is equal to this, that is what we have learnt in the last class. So, this into this from that solenoidal vorticity field, we can write that omega j u I del x j, okay, bar. Okay. So, essentially you see the gradient of these, the gradient of this means what? So, this order of this particular term once again is ut square by L, means order of this particular term is the gradient of Reynolds stress. So, gradient of Reynolds stress, so that means this particular term gradient of Reynolds stress divided by 1 by L. So, that means the order of magnitude, so order of magnitude of this particular term is going to be ut square by L square. Okay. That is what it says. So, that means if this is ut square by L square, this should be ut by L. So, once again ut cube by L cube is the order of magnitude of this term. Okay. So, this is order of magnitude L cube by ut cube by L cube, all these terms similarly ut cube by L cube. Okay. And order of magnitude of this term, of course, it is ut cube by L cube. Okay. So, what is the order of magnitude of these two terms? Okay, that is what we have to find out. If you see the order of magnitude of this term, that is basically your nu into ut square by L cube. Okay. So, this is L and this is what? This is also order of nu ut square by okay. So, this is, there is a mistake here. Okay. So, this is should be L to the power 4. Okay. So, that means you see what we can do, we can write this as nu ut cube by L cube, then so essentially this particular order can be written as, you see, nu by ut L and ut cube by L cube. Similarly, this particular order can be written as ut L ut cube by L cube. Okay. So, essentially you see 1 by REL into ut cube by L cube into ut cube by L cube are there in these two terms. So, that means if we would like to simplify this equation, then if we like to simplify this particular equation, then only the viscous terms can be neglected from this equation, that is what it says. Okay. That means our simplified equation is going to be, okay. So, simplified equation for large Reynolds number of codes, for large value of REL we get or is, okay, what, that uj del xj, okay, equals to this, this particular term, okay, or these two term once again we can write as, these two term can be written as, these two term we can combine the way it was, that is sigma I del uj omega I bar, okay. These two term we are once again combining, okay, just to accommodate all the terms here, plus, because these two terms we got from this. So, we can write this in this fashion itself, and plus you see these all other term. So, other terms Sij plus omega j small Sij bar plus plus 1 no, this is done, this is the mixed term which is already considered. So, this is what the equation will get. Okay. We have to make sure that we have collected all the terms, I hope so. Okay. So, all right. So, this is what these are the terms which are contributing maximum to the change of mean entropy in a flow. Now, you see one more thing which can be done here. Actually, if you consider a 2D flow, okay, for which the gradient with respect to del x3 is 0, 2D flow, then this particular part will also be 0. Okay. So, this particular part in that case can be 0. Okay. So, simplified equation for, in this case the simplified equation for I is equal to 3, you can write it. Okay. So, for 2D flow, for 2D flow or for 2D flow, the equation for 3 can be written as uj half 3 del xj equals to, once again this can be written as your minus del uj omega I means omega 3 uj omega 3 bar del xj, okay, plus we can write this as uj omega 3 bar del omega 3 del xj, okay, plus only one more term is going to be there, that is your 3 omega j s 3 j. Okay. So, this is the equation, okay, because the other terms first from the order of magnitude analysis, the viscous terms are going to be 0. Next, if we consider the 2D flow for which the del x 3 is gradient of del x 3 is going to be 0, and only the mean vorticity, that this is what is going to be there. So, for that the equation is this. Now, this particular part also can be 0, provided we consider the change of scale is going to be negligible, okay, because this is associated with change of scale. That is what we have argued in some previous class, right. So, then that also can be neglected. So, we will be left with only this particular equation, okay. All right. So, this is what is our kind of mean entropy equation, okay. So, now how we can find out the equation for turbulent entropy. Turbulent entropy means the mean square turbulent vorticity, okay. So, mean square turbulent vorticity means turbulent fluctuating vorticity, okay. So, we will do one thing. So, we will skip the derivation here, but the idea I just wanted to tell you. First, you consider the that instantaneous vorticity equation, then multiply by instantaneous vorticity to that equation, then use the Reynolds decomposition and time average that equation. After that, you subtract the subtract the mean entropy equation from that particular equation. If you do that, then we are going to get the mean or turbulent entropy equation, or turbulent mean square equation for omega I bar, okay, which can be referred as turbulent entropy equation, okay. So, what is the procedure? Once again, first you have to consider the instantaneous vorticity equation, multiply that instantaneous vorticity equation by omega I, then time average that equation, whatever you got from that equation you subtract the mean entropy equation. The way we have done the turbulent kinetic energy equation, derivation of the turbulent kinetic energy equation, in the same way the entropy equation, derivation of this turbulent entropy equation also possible, okay. So, anyway you try, and the derivation I am going to share you later on by email, okay. So, this is what we have to do to get this equation, and if I write this equation, then this is what we will get it here. So, the equation for this is basically, let me write directly the outcome of this procedure what I mentioned just now, equals to minus u j omega I bar. This is what the gradient production as we have mentioned, okay. This is found, this term is found with opposite sign in the mean entropy equation as well, okay. So, then that half del u j omega I bar, okay, del x j, this is what you are going to get it. Then you are going to get omega I omega j small s I j bar, okay, plus you are going to get omega I omega j bar capital S I j, okay, plus that mixed vorticity term j omega I small S I j, okay. That is what we are going to get. Then we are going to get another two term, that is viscous term. So, that is viscous diffusion. So, viscous diffusion term is going to be del 2 half omega I bar del x j minus nu omega I del x j omega I del x j bar. Okay. So, 1, 2, 3, 4, 5, 6, 7. Okay. So, these are the terms in the right hand side which are responsible for the change of the turbulent entropy in a turbulent flow, all right. So, what are these terms? That is what we need to understand. Okay. So, see this particular term, we told that this particular term is known as gradient production. This term is just like your this term, if you can remember, this term just like your production of turbulent kinetic energy, what we have got in the turbulent kinetic energy equation. Okay. So, this term just like your minus u I u j del u I del x j. Okay. In turbulent kinetic energy equation, this term and this particular term is just like this. Okay. So, this particular term therefore, we call gradient production of entropy. Okay. This particular term is known as gradient production of entropy, that is what we have said, and this is what, this is your kind of transport term, transport by turbulent fluctuation. Okay. So, which was u I u j bar. Okay. Half this was, if you can remember, this particular term was our del u I u j bar. Okay. So, transport of kinetic energy, transport of turbulent kinetic energy, okay, by the turbulent velocity fluctuation. Okay. Similarly, this is the transport of turbulent entropy by this turbulent velocity fluctuation u j. Okay. So, these two terms you understand, this is just your transport of this particular term is transport of that turbulent entropy. Okay. And this particular term is production of turbulent entropy by stressing of the fluctuating vorticity by the fluctuating strain rate tensor. Okay. Similarly, this particular term is the production of turbulent entropy by stressing of the turbulent vorticity by mean strain rate tensor. Okay. And this is the mixed this is the mixed production term. We have said the way the turbulent vorticity is produced by the fluctuating strain rate tensor in the case of mean entropy equation, in the same rate this the fluctuating or the turbulent entropy is also going to be produced by the interaction of this turbulent vorticity and or by the by the turbulent strain rate tensor, okay, with the interaction of the the mean vorticity as well as fluctuating vorticity. Okay. So, this is known as your mixed production term, as we have already mentioned, and this is the diffusion, this is the diffusion of the entropy, and this particular term is the dissipation. Okay. So, these are the so this is dissipation, diffusion, okay, mixed production, then production by stressing, production by stress, production by mean strain rate tensor, production by stressing by fluctuating strain rate tensor, and this is your transport by turbulent velocity fluctuation, and this is your gradient production. So, these are the kind of different terms which are involved in the change of this particular quantity in the left hand side. Okay. So, now what we have to do, which terms are, suppose we would like to know which terms are important in these particular equations, okay, because this equation is almost like intractable. So, we need little approximation to understand further. Okay. So, to do that approximation, we need to go ahead with the order of magnitude analysis of this particular equation. But to do the order of magnitude analysis, we have to know what will be the order of omega I into omega I, or what will be the order of omega I. We have not yet understood, we have not yet discussed that. Okay. And this order of this particular term we have already said that can be written as ut square by L, gradient of Reynolds stress. Okay. So, that is perhaps possible, but we do not know the we do not know the order of omega I into omega j. Okay. Although we know the omega into omega I, we may be knowing, but what is the order of omega I into omega j, that also we have to figure it out. Okay. So, there are many terms which need to first know what are the order of magnitude of these particular terms, okay, before we go ahead with the order of magnitude analysis for for a budget of this enstrophy equation, okay, in terms of order of magnitude analysis. Okay. If we would like to do that, let us start doing it here. Okay. So, we need to find out the order of magnitude of omega I into omega I. So, what will be the order of magnitude of this term, or omega I omega j, what will be the order of this term. Okay. So, these are the things we have to find it out before we proceed further. Okay. Now, so to find out the order of magnitude, first let us start with the definition of omega I, which can be written as epsilon I j k and r k j, okay, whether where r k j is the rotation tensor. Okay. We have already defined that. Okay. So, you see here j and k are dummy indices here. Okay. Similarly, omega I we can write since these two are dummy indices, we can write m n r n m, same thing. Now, to find out the omega and omega I and omega I, what we can do, we can just multiply these two equation, right. Let us say it is your equation 1 and equation 2, then you can just multiply these two equation to find these, and in the right hand side you will get I j k r k j, okay, epsilon I m n r n m. Okay. So, this is what we can write. Now, you see here what we are getting, epsilon I j k epsilon I m n. So, there is a relation in tensor algebra which is known as epsilon delta relation. We have to use this relation for further simplification. So, what we can do, these two relation can be written as delta j m delta k n minus delta j n delta k m, okay, into your r k j r n m. Okay. So, this particular relation, this epsilon I j k into epsilon I m n is equal to this is known as epsilon delta relation. Okay. Now, what you can do, you can just distribute this. So, or okay, can be written as, you see, delta j m r k j delta k n r n m minus delta j n r k j r k j r k j delta k m r n m. Okay. So, you see this particular part and this particular part, similarly this and this. Okay. So, this is going to be non-zero only when j is equal to m. That means, this is going to be your r k m, and similarly this is going to be non-zero when k is equal to n. So, this is also your r k m minus this is going to be non-zero when j is equal to n, that means r n r k n. okay, and this is also going to be non-zero when k is equal to m, right. So, r n k. Okay. So, this essentially both are, see here k and m dummy index, k and m dummy index, k n dummy index. So, this essentially you can write as r k m and r k m minus or plus you can write r k k n, sorry, r k n and if you exchange the indices here n k, then we can write it as minus of that. So, that is r k n, then minus and minus become plus. So, essentially both are dummy indices. So, this is essentially nothing but your twice into r I j r I j. Okay. This is what we can write. Okay. So, that means it says that omega I into omega I bar essentially can be written as twice r I j bar. Okay. That is what this exercise says. Okay. Now, we need to do another exercise. So, another exercise you see, we know small s I j minus let us write small r I j. Okay. We know the expression of s I j, expression of r I j, okay. And this is nothing but your, if you write this, so this can be written as half, okay, or this is basically 1 by 4 del u I del x j plus del u j del x I whole square minus 1 by 4 del u I del x j minus del u j del x I whole square, right. So, if you go ahead with the algebra, then essentially you are going to find it out the last term, that is j del u j del x I. Okay. So, essentially this minus this we can write simply as, this can be written as del u I del x j del u j del x I, and this can be once again written as u I u j del x I del x j. Okay. How? So, that is what we have to figure it out. Okay. Let us start with these. So, if we start with these del u I u j del x I del x j equals to, we can write del x I and then del u I u j del x j is this, right. So, this can be written as del x I del x I u I del u j plus u j del u I del x j, and this part becomes 0 from continuity. You see, this part becomes 0 from continuity. So, essentially we are left with del x I u j del u I del x j. Okay. So, this if we write, we can write this as del u j del x I del u I del x j plus another term is going to be there, that is your u j del 2 u I use a del 2 ui del xj del xi. Okay. Now what you can do, once again this last part del uj del xi plus into del ui del xj plus this can be written as uj. You see, I can write this as del xj and I can write this as del ui del xi, which is once again 0 from continuity. So, this is once again 0 from continuity, right. So, essentially we are left with, that means this is equal to del uj del xi del ui del xj, which is nothing but this. So, that means this is equal to this is equal to this. So, that means we can write that Sij minus Rij, Sij into Sij minus Rij is equal to the double derivative of Reynolds stress. So, essentially what we can write, this is equal to this is equal to this, essentially this. Okay. So, that means you see the order of this term, or let me write another line. So, Sij bar minus Rij bar equals to, I can write del ui uj bar del xi del xj, right. Now, what is the order of magnitude of this? Now, order of magnitude of this term, you know, epsilon is equal to twice nu into Sij into Sij is equal to 15 nu into URMS square by lambda square, okay, or lambda g square, as you can remember. Okay. So, that means order of this term is nothing but your ut square by lambda square. Okay. We do not know the order of magnitude of this term. What is the order of magnitude of this term? Order of magnitude of this term definitely ut square by L square. It should be 2, right? Yeah. Ut square by L square, right. Now, this ut square by L square we can just little bit manipulate. Ut square by lambda square, I can take lambda square by L square. Okay. And you know from our previous class that lambda by L scale with REL to the power minus half. So, that means this particular term here we can write as 1 by REL. Okay. So, that means for large Reynolds number, this value or value of the or order of magnitude of the right hand side term is negligible. Okay. Since we do not know the order of this term, then order of this term and order of this term should be same. So, in that case we can write from this equation. So, from this equation it implies that Sij bar equals to Rij bar, okay, on an approximate basis, please do understand. Okay. So, first we have got, so you see, so this is what is our, so that means you see from here you have got omega I into omega I is equal to this. So, from this what you can write that since this, so twice small Sij bar, okay. That is what you can write. And then what is the order of magnitude? So, from this you can find the order of magnitude. Okay. So, order of magnitude of this term is clearly ut square by lambda square, okay, because this is equal to this and order of this we know from the dissipation, okay, which is nothing but ut square by lambda square. Okay. So, order of magnitude of this term is this. So, order of magnitude of this of the we can write as this. Okay. So, this is what this is what we can argue from this simple algebra. Okay. So, another interesting point, you see epsilon is equal to what do you know? Another interesting point to note here, we know the dissipation epsilon is equal to twice nu small Sij bar. Okay. Twice small Sij bar is equal to what? So, from this you see, from this you can see epsilon is approximately equal to, of course, for large Reynolds number only, it is going to be nu into omega I bar. Okay. That is what it says, all right. So, we have got the order of magnitude of omega and omega I. So, omega I is ut by lambda, epsilon which is equal to this, and Sij bar can approximately be written as Rij, okay, and for a very large Reynolds number, of course. Then at very large Reynolds number, this epsilon can be written as nu into this. Okay. So, that is what we got. Now, interesting point here to note, we have got the diagonal term. What about the non-diagonal terms of this particular quantity? Okay. What will be the value of this? So, the non-diagonal term of this particular product is going to exist only at non-zero value of stranded tensor, non-zero value of mean stranded tensor. If the mean stranded tensor of the mean stranded tensor is non-zero, of diagonal terms are non-zero, then only these terms are going to survive. So, this then can be written as ut square by lambda square a delta I j plus b I j S I j into lambda by L plus other terms. So, that means what we would like to say that of course, when the I is equal to j, you see from this equation I is equal to j, SII is equal to 0 from the continuity equation. So, all other part of this side are 0, we are left with only A into ut square by lambda square. A is of order of 1 from this analysis whatever I have got. So, that means that omega I into omega j is in that case ut square by lambda square. But off diagonal term, so when this Sij value is non-zero, that means for off diagonal term, then it is going to be order of magnitude is going to be ut square by lambda square into this term. Okay. Why is this? Why this particular multiplication factor come here? So, that is very important to understand, because the scale of this is ut by L, right, and your scale of your omega I into omega j, let us say ut square by lambda square. Okay. So, the time scale of these, I mean the time scale which is contributing to these and time scale which is contributing to these are way apart. So, their correlation depends. So, their correlation depends on their ratio of their time scale, which is nothing but your lambda by L. Okay. So, which is nothing but your lambda by L. So, that means this is equal to ut square by lambda square into Sij, scale of Sij, Bij in that case of order of one quantity. That means the order of omega j Sij, if you would like to find it out, then it is going to be order of it is going to be order of, sorry, Sij should not come here, okay, I am sorry, delta Ij plus Bij into lambda by L we have prorated. So, that means if you would like to find out the order of magnitude of this product, then the order of magnitude of this we can take as this into order of magnitude of this, which is ut by L, since the order of since the eddy which is contributing to this time scale of that eddy and time scale of this eddy are different. Okay. So, their contribution or their product should be proportionate with their ratio of their time scale, which is nothing but this. Okay. Time scale of this large eddy so time scale of the large eddy, sorry, small eddy is this and this large eddy is this, right. So, which is time scale of the small eddy is this, time scale of the large eddy, ratio of their time scale is this, which is proportional to Re to the power minus half. Okay. So, for very large Reynolds number their correlation is very small. Okay. So, that means order of this particular quantity needs to be prorated by the ratio of their time scale, if their time scale are way apart. That is what has been done here. So, the order of magnitude of this particular term then is going to be this. Okay. So, with this now we can proceed with the order of magnitude analysis of this particular equation. Okay. So, let us do it here. So, if you go ahead the order of magnitude of term by term of the turbulent entropy equation, first let us find out the order of magnitude of this particular term. Okay. So, order of magnitude of this particular term is going to be order of magnitude of this term. So, this is ut by L into this is going to be ut square by lambda square, which can be written as, let us write it as ut cube by lambda cube then lambda by L, okay. And lambda by L, see this is order of this into order of this ut cube by lambda cube into this is REL this, right. That is what we get, right. Now, order of next term. So, next term is minus u j omega I del x a, order of this term. Order of this term is what? Gradient of Reynolds stress u t square by L. Okay. So, this is going to be u t square by L into this is going to be u t by L square, right. So, this is order of u 2 cube by lambda cube and lambda cube by L cube, order of u t cube by lambda cube 1 by or R e L minus 3 by 2. Okay. This is what is the order of magnitude of the second term. Order of magnitude of the third term, that is minus half del u j omega I del x j. Okay. This particular term can be, this particular term we can write as u j into that omega I into omega I del x j. So, if we find the order of magnitude of this particular term, this is going to be order of u t by L u t square by lambda square, okay, which is of the order of u t cube by lambda cube and lambda by L, which is of the order of u t cube by lambda cube R e L minus 2. Okay. Then the next term is omega I omega j small s I j bar. This should be of the order of So, here you see the eddies which is contributing to omega I omega j and eddies which is contributing to S I j are of the same time scale. So, that is why there is no need of prorating like whatever we have done lambda by L, keep it in mind. Okay. So, that means this particular order of magnitude of this particular term is going to be u t square by lambda square and this is u t by lambda. Okay. So, this is going to be your u t cube by lambda cube into 1. Okay. So, this is what you get it for this particular term. And what about the next term which we have already done. So, next term is your omega I omega j capital S I j bar. So, this we have already argued that this is going to be u t square by lambda square into u t by L into that length scale time scale ratio needs to be multiplied because their frequency is way apart to find the actual order of magnitude of this particular term. So, this is going to be u t cube by lambda cube if I take. So, then I can write this as lambda square by L square which is order of u t cube by lambda cube into R e L minus 1. Okay. So, then we have the another term which is your mixed production term. So, mixed production term is your j omega I Sij. Okay. So, omega I Sij, what is this? So, this particular term, if you can remember, we can write it as del, del u Sij, sorry, del omega u del xj. Okay. So, if you can remember, so that particular term we have already removed. So, it was actually your it was essentially your omega j del u I del xj. Okay. So, this can be written as del omega j u I del xj. Okay. That is what this is. So, and this is nothing but your omega j Sij. Okay. That is what we have argued in some previous class. Okay. So, this particular order of magnitude is essentially the order of ut by L into this is Reynolds stress gradient. So, that means ut square by L square. Okay. So, this is going to be order of ut cube by L lambda cube, ut cube by lambda cube into lambda cube by L cube, which is equal to order of ut cube by ut cube by lambda cube into REL minus 3 by 2. Okay. Now, we are left with only the last two viscous term. So, last two viscous term if we write, we are left with the order of magnitude of this term del 2 half omega I bar del xj minus nu del omega I del xj. Sorry, we are supposed to find, I am sorry. So, this is going to be, we are going to find out the order of magnitude of this particular term. So, order of magnitude of this particular term, we can write it as ut square by lambda square 1 by L square, which is order of nu is there, we are forgetting nu. Okay. So, order of nu ut L, and this is you are going to have ut cube by lambda cube, let us say, and lambda cube. So, one lambda has gone above, one L has come up here. So, this is what it is, which is nothing but order of your so this is REL to the power minus 1, this is REL to the power minus half. So, that means ut cube by lambda cube into REL minus half minus 1. So, minus 3 by 2. Okay. And the last part once again del this omega I del xj del omega I del xj. Okay. Now, here we have a trouble, we do not know the order of magnitude of this gradient. Okay. So, what will be the order of magnitude of this gradient, we do not know. All right. So, if you see this equation now, if you see this equation, okay, we have got the order of magnitude of each and every term, and some term order of magnitude have come with respect to Reynolds number 1 by REL. Okay. For example, this term, this term, this term, this term, this term, this term. Since we do not know the order of magnitude of this term, we have to keep this term. But if we consider, if we consider the Reynolds number to be very, very high, you see, if we consider the Reynolds number is very, very high, then this particular term is negligible. Similarly, this term is negligible, this is also negligible, negligible, this is going to be there, this is negligible, this is also negligible, this is also negligible, because all are function of 1 by REL. So, for very high Reynolds number, the order of magnitude of all these terms except this term and the order of magnitude of the last term which we do not know can only be kept in the turbulent entropy equation. Okay. So, in that particular case, that means we can make it all these term, all these term 0, 0, 0, 0, this is also 0, this is also 0, this is going to be there, because order of magnitude of this particular term is way high as compared to all other terms, and since we do not know the order of magnitude of this term, so this term also needs to be kept. So, finally, from this equation what we get, so finally, we get from our order of magnitude analysis, what do we get? We get omega I, omega j, small sij bar equals to nu into bar. Okay. So, this is what is our simplified entropy, turbulent entropy equation for very high Reynolds number, keep it in mind. Okay. So, there are some interesting observations to look at from these particular equations. You see the right hand side omega I, del omega I del xj, del omega I del xj, which is quadratic. That means, the right hand side term is always positive. If right hand side term is always positive, that means this term is also going to be positive. Since this term is going to be positive, that means vortex tracing should be more as compared to vortex squeezing. Okay. That means, the stressing will be more, because in that case it is going to be positive then. For squeezing it is going to be negative. So, vortex squeezing on an average is more as compared to vortex stressing is more as compared to vortex squeezing. That is what this equation says. Okay. And the vortex stressing term will try to generate vorticity in such a fashion such that this dissipation term allows it. Okay. It cannot, the vortex stressing term cannot generate vorticity the way it like, because that will be kind of balanced by the dissipation term. Okay. So, the vortex stressing by this fluctuating strain rate tensor, increase of this turbulent entropy by this vortex stressing of this vortex stressing by this turbulent strain rate tensor cannot go very high, because that is going to be killed by your this dissipation term. So, these are the two main things which we learned from this equation. So, we would like to stop it here for today. We will again discuss from this point onward in the next class. Okay. Thank you.